Hello all, welcome back to the course on computer graphics. Uh, we've started with the module 4. We've already seen some of the three-dimensional concepts and some of the three-dimensional display methods. So then we come into three-dimensional object representations. Okay, so the there are different kinds of objects that can be displayed on a 3D screen, that is trees, flowers, clouds, roads. So there are different kinds of objects, so it requires different methods to describe an object. Okay, so if you want to uh, display an object, it may require more than one method to display it. Okay, so to produce realistic displays of scenes, we need to use representations that accurately model object characteristics. So you use different object representations like polygon, quadric surfaces, spline surfaces, then some other construction techniques, procedural methods, um, like that. There are many types of three-dimensional object representations. Basically, these representation schemes for solid objects are often divided into two broad categories, that is boundary representation and space partitioning representation. So the boundary representation describe a three-dimensional object as a set of surfaces that separate the object interiors from the environment, and space partitioning representations are used to describe even the interior properties by partitioning the spatial region containing an object into a set of small non-overlapping contiguous solids. Okay. So these are the basic or this is a broad classification of object representations. The different object representations come under that may not fall neatly into one or the other of these two categories, but broadly you classify it as broad boundary representations and space partitioning representations. Okay. So we are going to see only some of these object representations. For you in your syllabus, you have only polygon surfaces and quadric surfaces. First we will see polygon surfaces. Okay, so polygon surfaces, it is a boundary representation. Boundary representation is describes three-dimensional objects as a set of surfaces that separate the object interior from the environment. So it will be represented using some surfaces. If you take a cube, you can see you can represent a cube using as a polygon surfaces, means that only the surface representations will be provided, the interior details won't be there. So it is just uh, described as surfaces which separates the outside environment from the inside of that object. Okay, so it is a boundary representation. It's the most commonly used boundary representation for three-dimensional graphic objects, and it is a set of surface polygons that enclose the object interiors. Okay. Many graphic systems store all object descriptions as a set of surface polygons. Okay, and this simplifies and speeds up the surface rendering and display of objects, since all surfaces are described with linear equations. For this reason, polygon descriptions are often referred to as standard graphic objects. Okay. Basically, it is used in all kinds of graphic system. That's why it's called as a standard graphics object, because it actually simplifies and speeds up the display. Okay. So for polygon surfaces, you can um, specify the polygon surfaces with a set of vertex coordinates and associate attribute parameters. Okay. So as information for each polygon is input, then the data are placed into tables that are to be used in the subsequent processing, display and manipulation of the objects in the scene. So we use some tables called polygon tables to store this set of vertex coordinates and the associated attribute parameters. Okay, that is polygon tables. So uh, when you input the information of a polygon, then when you input an information of a polygon, then this data is placed into these polygon tables. Okay, and the polygon data tables can be organized into two groups mainly. They are geometric tables and attribute tables. Okay, geometric data tables contain vertex coordinates and parameters to identify the spatial orientation of the polygon surfaces, and attribute information or the attribute table contains the attribute information for an object, that is parameters specifying the degree of transparency of the object and its surface reflectivity, texture characteristics, etc. Okay, so there will be polygon data tables will be there. The polygon data tables can be organized into two groups, that is geometric data tables and attribute tables. Geometric data tables will contains the values of or the set of vertex coordinates and parameters to identify the spatial orientation of the polygon surface, and attribute table will contain other parameters specifying the degree of transparency, the texture, surface reflectivity, etc. Okay, and a convenient organization for storing geometric data is to create three lists, that is a vertex table, an edge table and a polygon table. That is a most convenient way to store the geometric data. Okay. Uh, you use three lists: vertex table, edge table and a polygon table. There are other methods can also be used. In some methods the objects this geometric table use only vertex table and a polygon table, but this scheme is less convenient, and some edges could get drawn twice. Then another possibility is to use only a polygon table, but again this is not convenient, but because it duplicate coordinate information, etc. So the most convenient method is to, or which is which we will see it later, that is when you have to process these displays later, it is more better to use this method, that is you can store geometric data tables as three lists, that is a vertex table, an edge table and a polygon table. Okay, so the vertex table will have all the coordinate values for each vertex in the object, and they are stored in this vertex table, and the edge table contains the pointers back into vertex table to identify the vertices for each polygon edge, and the polygon table contains the pointers back into the edge table to identify the edges for each polygon. When you see this figure, you will understand more better. So you here for this polygon, you have three tables, three lists, which stores the geometric information. That is vertex table. Vertex table contains the vertex information. That is this polygon has vertices v1, v2, v3, v4 and v5. So v1 is has the coordinates x1, y1, z1. v2 has the coordinates x2, y2, z2. Similarly, all the information about the vertices are stored in the vertex table. Then there is an edge table. Edge table contains the information about the edges. That is if you take this polygon, you have the edges e1, e2, e3, e4, e5 and e6. So it basically gives the information about which vertices forms or which vertices are there in the edge E1. So E1 contains V1, V2. E2 contains V2, V3. So it is basically the representation of the edges and its corresponding vertices. And there will be a polygon table or a polygon surface table. It simply defines which all edges form a surface. So here in this polygon there are two surfaces, S1 and S2. S1 is formed by the edges E1, E2 and E3. So that is shown here, and S2 is formed by the edges E4, E5, E6 and E3. So that is shown here. Okay, so this is the geometric representation of a polygon using polygon tables. So this is geometric tables, and there will be also attribute tables. Okay, so also we can add some extra information to this to these geometric tables. We can add some extra informations like this. Okay, so here we could expand the edge table to include forward pointers into polygon table, so that the common edges between the polygon could be identified more rapidly. So here the edge table here is this is the edge table. Edge table here is extended by adding some information about the surfaces. So here it simply means that this edge E1 having the vertices V1, V2 is in the surface, which is a part of the surface S1. So similarly, if you take E3, it is a part of the surface S. If you take E3, it is a part of the surface S1 and S2. So it will be easier to identify which are the edges that connects two surfaces. Okay, so for that you can even expand or you can add extra information to this data table. So similarly you can do many other expansions on this data tables. Okay, so and additional geometric informations that is usually stored in data tables include slope of each edge and the coordinate extents for each polygon, etc. Okay, since the geometric data tables may contain extensive listing of vertices and edges for complex objects, it is important that the data be checked for consistency and completeness. So here this is a here the example shows a simple polygon surface, but in most cases when you are representing a polygon using data tables, then the there will be an extensive listing of vertices. There will be many vertices, many edges. So it is likely to have errors in the data table. So it is always important to check the data for consistency and completeness. Okay. So that's polygon tables. Then um, you have plane equations. That is, to produce a display of three-dimensional object, we must process the input data representations for the object through several procedures. Okay, so these processing steps include transformation of modeling and world coordinate descriptions to viewing coordinates, then converting it into or mapping it into device coordinates, then identification of visible surfaces, and then the application of surface rendering procedures. Okay, so this is how, these are the steps basically used for displaying a three-dimensional object. Okay, so these are the procedures. First, you have to transform the modeling and world coordinate descriptions to viewing coordinates. Then you have to move it to device coordinate. Then you have to identify the visible surfaces, and then the application of surface rendering procedures on that display. Okay, so this is the procedure. So for some of these processes, we need the information about the spatial orientation of the individual surface components of the object. So this information is obtained from vertex coordinate values and line equations that describe the polygon planes. Okay, so there are some equations that gives the information along with the vertex coordinate values that we are saving using polygon tables. You also need some of the line equations to understand the spatial orientation of the surfaces. Okay, so for that you use some plane equations. So the equation for plane surface can be expressed in the form uh, given here, that is ax plus by plus cz plus d equal to 0. Okay, so this is the equation for plane surface, and here x, y, z is any point on the plane, and the coefficients a, b, c and d are constants describing the spatial objects of the plane. Okay, so xy, if you take any point x, y, z on the plane, this should be this equation should be satisfied. Okay, ax plus by plus cz plus d equal to 0. Okay, and uh, uh, so this is the plane equation, and now to find the values of a, b, c and d, we select three successive polygon vertices, x1 y1 z1, x2 y2 z2 and x3 y3 z3. You take three vertices of a polygon and solve a set of simultaneous linear plane equations for the ratios a by d, b by d and c by d. Okay, you simply solve this equation, and then you get a by d into xk plus b by d into yk plus c by d into zk equal to -1, where k is 1, 2, 3. Okay, that is basically you do a by d x1 plus b by d y1 plus c by d zk equal to -1. We solve that, and similarly for a by d x2 y2 z2 and x3 y3 z3, you solve it, and then as the solution for that equation, um, uh, can be obtained in determinant form using some Cramer's rule as A equal to 1 y1 z1 1 y2 z2 1 y3 z3. B is equal to x1 1 z1 x2 1 z2 x3 1 z3, and C as x1 1 y1 x2 y2 1 x3 y3 1, and D is x1 y1 z1 x2 y2 z2 x3 y3 z3. Okay, so this is the values for A, B, C and D. Okay, so expanding this determinants, we can write the calculation for plane coefficients in the form A equal to y1 into z2 minus z3 plus y2 into z3 minus z1 plus y3 into z1 minus z2, and B as z1 into x2 minus x3 plus z2 into x3 minus x1 plus z3 into x1 minus x2, and C as x1 into y2 minus y3 plus x2 into y3 minus y1 plus x3 into y1 minus y2, and D as minus x1 into y2 z3 minus y3 z2 minus x2 into y3 z1 minus y1 z3 minus x3 into y1 z2 minus y2 z1. So these when you expand that this determinants, you get this equations for the plane coefficients A, B, C and D. As the vertex values and other informations are entered into polygon data structure, values for A, B, C and D are computed for each polygon and stored with other polygon data. So, once you have entered the values of vertices, so when you first input the information about the polygon, you enter the coordinates of the polygon, okay, vertices of the polygon. So when you get those vertices, the coordinates of the vertices, you can calculate the values of A, B, C and D, and you can store it with other polygon data in the geometric table. Okay, so that is simply plane equation, and also the orientation of a plane surface is in space can be described with a normal vector. Okay, so that is if you to understand in what orientation a particular surface is placed on a on the 3D view, you have to understand the normal vector. So, normal vector is a vector perpendicular to this surface. Okay, so here if you see this image, you can understand here is a here is an object and this object has a normal vector n which is perpendicular to this surface, and this n is equal to ABC. So, the surface normal vector has the Cartesian components ABC. This ABC are the plane coefficients that we have found here. Okay, so once you have found the plane coefficients, you can the normal vector is simply the Cartesian components of components A, B, C. Okay, so from that you can understand the orientation of the plane or the surface that you are going to display. Okay, so that is about the orientation. Then the plane equations are all used also used to identify the position of spatial points relative to the plane surfaces of an object. So, for any point x, y, z not on a plane with parameters a, b, c, d, we have ax plus by plus z plus d not equal to 0. Okay. Uh, the plane equation is ax plus by plus z plus d equal to 0, which means that that x, y, z should be a point on the surface. If for a point which is not on the surface, it should be a value not equal to 0. Similarly, to identify the surface, whether it is this inside of the surface or outside of the surface, to check whether the point is inside the surface or outside the surface, you can identify this using uh, by checking the sign of this equation. That is, if ax plus by plus cz plus d is a negative value or less than 0, then that point x, y, z is inside the surface, and if the value x plus by plus z plus d is greater than 0, that means it is outside the surface. So, simply you can understand the what you say, which face, the inside face or the outside face of a surface is visible. Okay, so this could be understand by using this simple equation. Okay, so these inequality tests are valid only in a right-handed Cartesian system, and this plane parameters or the plane these values a, b, c, d were calculated using vertices selected in a counterclockwise order when viewing the surfaces in an outside to inside direction. So, these are some of the um, um, things that we should take care of. Okay. That is plane equations. Then we are going to see polygon meshes. Okay, so we have told that you can we have said that a object can be represented as polygon surfaces and you can display it. Okay, so for some objects, the surfaces are tessellated or tiled to produce a polygon mesh approximation. Okay, so that means if you see this figure, you can see that here this cylinder is represented as a polygon mesh. Okay, so here it is represented using so many polygons. See, this is styled to produce a polygon mesh approximation, and such representations are common in design and solid modeling applications, since the wireframe outline can be displayed quickly to give a general indication of the surface texture structure. Okay, so the realistic rendering can be produced by interpolating shading patterns across the polygon surfaces to eliminate or reduce the presence of polygon edge boundaries. Okay, so wireframe will be easier to produce, and by shading patterns or using some surface rendering techniques, you can simply hide those lines or these polygon edges. And the polygon mesh approximation to a curved surface can be improved by dividing the surfaces into smaller polygon faces. So, here it is a curved area, right? So, this object has a curved area, and here to improve the uh, display the polygon approximation to a curved surface can be improved by dividing the surface into smaller polygon faces. So, if you still again divide it into some more strips or some more number of polygon facets, then it will be more accurate or more better curved area. Okay, so that way polygon meshes are used to display objects. Okay, so here we are going to see only some methods of in which the polygon meshes are used to display the objects. So one type of polygon mesh is the triangle strip. Okay, so this is a figure for triangle strip. So here the object that is to be displayed is divided into some triangular strips, and this function will produce n minus 2 connected triangles given the coordinates for n vertices. So, if we are given n vertices, suppose you are given some 10 vertices, then n minus 2, that is 8 triangles will be triangular strips will be created, connected triangles will be created. Okay. Similarly, you can use another function, quadrilateral mesh. So this is a figure of a quadrilateral mesh. Here this mesh generates n minus 1 by m minus 1 quadrilaterals given the coordinates for n by m array of vertices. So if you are given 5 by, here it is 5 by 4 matrices, or a matrix array, it's a matrix array of 5 by 4 vertices, and so it will produce it will have some n minus 1 by m minus 1, that is 4 by 3, that is 12 quadrilaterals will be created. Okay, so will be generated. Okay, so that are some polygon meshes that is used. Okay, that's all about the polygon surfaces, and now we will see about the quadric surfaces. Quadric surfaces are a frequently used class of objects which are described with second degree equations, that is quadratic equations. Okay, so these are objects that are described with quadratic equations. Examples are spheres, ellipsoids, tori, paraboloid, hyperboloids. So these are some of the examples of quadratic surfaces. We are going to see the representation of spheres and ellipsoids and torus here. Okay. And the quadratic surfaces, particularly sphere and ellipsoid, are a common element of graphic scenes, and they are often available in graphic packages as primitives from which more complex objects can be constructed. Okay, so this is a common thing in all the graphics packages, and we are going to see the representation of quadratic surfaces like spheres, ellipsoids and torus here. Okay, so sphere in Cartesian coordinates, a spherical surface with radius r centered on the coordinate origin is defined as the set of points x, y, z that satisfies the equation x square plus y square plus z square equal to r square. Okay, so simply you can define a spherical surface with radius r and the center at origin. Okay, this is the x, y, z axis. It is the sphere has the center at the origin, then and it has a radius r, then and one point on the sphere is defined using the coordinate values x, y, z. Then you you have to satisfy the equation x square plus y square plus z square equal to r square. That means any point on the sphere surface of the sphere, that is x, y, z, can be any point on the surface of the sphere, and if it is a point on the surface of the sphere, then it should satisfy this equation x square plus y square plus z square equal to r square. And we can also describe this spherical surface in parametric form using latitude angle phi and longitude angle theta. That is, this is the latitude angle and this is the longitude angle. So, the latitude angle phi and longitude angle theta can be used to define or describe a spherical surface. For that, you can use these equations, that is x equal to r cos phi cos theta and y is equal to r cos phi sin theta and z is equal to r sin phi, where phi is greater than minus pi by 2 and less than pi by 2, and theta should be greater than minus pi and less than pi. Okay, so this is the representation of a sphere using Cartesian coordinate equation and parametric form. Okay. So next is ellipsoid. Ellipsoid is a surface that can be described as an extension of a spherical surface. But here the radius will be different in different directions. That is, where the radius will be, there will be three radius. One in x direction, one in y direction and one in z direction. There will be different values for the radii. Okay, so this ellipsoid can be represented. Here again this ellipsoid is centered at origin and it has three radius, rx, ry and rz, and such an ellipsoid can be represented using Cartesian equation as x by rx the whole square plus y by ry the whole square plus z by rz the whole square equal to 1. So, any point x, y, z on the surface of this ellipsoid should satisfy this equation. And the parametric in parametric representation, this ellipsoid can be represented as x equal to rx cos phi cos theta, y equal to ry cos phi sin theta and z equal to rz sin phi, and again same, phi is the latitude angle and theta is the longitude angle. Okay, that is representation of ellipsoid. Next quadratic surface is torus. A torus is a donut shaped object as shown in this figure. This here this shows the shape along the x and y axis, and this is along the z axis. Okay, this donut has the value rx ry, that is the this distance. Okay, rx ry is this distance, and you have a value rz, that is this distance. Okay, you have three values rx, ry and rz, okay, along x, y and z axis, and you can represent a torus using this equation, that is r minus root of x by rx the whole square plus y by ry the whole square plus z by rz the whole square equal to 1, where r is any given offset value. Okay, so this is the Cartesian equation for a torus, and this torus are usually generated by rotating a circle or other conics with about a particular or a specified axis. Okay. And the parametric representation for torus are similar to those for an ellipse, except that the angle phi, that is our latitude angle, extends over 360 degree, and using the latitude and longitude angles phi and theta, we can describe the torus surfaces as a set of points that satisfy these equations, that is x equal to rx into r plus cos phi in cos theta, and y equal to ry r plus cos phi sin theta, and z equal to rz sin phi. Here the difference is that phi can be a value greater than minus pi or less than pi, and the theta extends from minus pi to pi. Okay. So, that's all about the quadric surfaces. Okay. There are many other object representations possible, like super quadrics, like super ellipsoids, then blobby objects, that is curved surfaces using blobby objects, then some spline representations. These are all possible, but we are not going to see this here. We in our syllabus only polygon surfaces and quadric surfaces are to be studied. Okay, so that's all about the object 3D object representations. Okay, thank you.